we're going to structure this tutorial in 3 parts, about 35 minutes each, and we'll have 2 7-minute breaks in between. And for questions, you should feel free to write your question in the chat, which will be monitored by someone of us throughout each of the parts. And then if there's additional questions or discussion with the speaker, you can talk live through each of the breaks by unmuting yourself then. So let's dive right into DeFi, or decentralized finance. When you hear decentralized finance, what comes to mind? Well, it's decentralized and it's finance, right? So blockchains first come to mind. And one of the most fundamental aspects of blockchains is that they enable the true ownership of digital assets. So on the blockchain, one gets property rights for digital assets. And what is one of the most basic rights? That is the right to transfer these assets. And so the magical thing about blockchain is that one does not lose control of their assets at any point in time during a transfer or any other transaction for this matter. So there's no counterparty risk. Now, for this talk, we won't need any other background on blockchains, but the key aspect that I want you to think about in this environment is that it is a naturally very computation and storage constrained setting. So we need to be as economical as possible with resource usage, and this is going to end up being crucial to our journey and to why AMMs are actually used. So what are some of the reasons why you might be interested in learning about DeFi? Well, as we said before, blockchain protocols enable true ownership. And once you have ownership of these assets, you have the possibility to exchange one asset for another. And so naturally, you have markets that are formed. So then you have the market design problem. And the simplest version of this is when you have two parties wanting to exchange some type of assets. Automated market makers are used exactly for this problem, to exchange assets and to figure out the price at which to do so. And they're very widely used on blockchains. So more than $2 trillion have been traded on AMM so far, and 20% of the trades on digital assets actually goes through AMMs. For those of you for whom financial applications maybe don't resonate as much, but the computer science and economics aspect hopefully gets you excited, let me just say that there is also non-trivial functionality in these automated programs, and the lessons learned from these novel mechanisms lead to insight that can be applied outside of the environment of blockchains. So these new primitives that we'll talk about, you can actually even think about these outside the context of blockchains. So again, the problem that we'll be interested in examining here is the asset exchange problem, where you have two assets and the running example will be that of Ethereum and US dollars, and you want to exchange one for another. The traditional market mechanism that has been used for this in traditional markets is that of a limit order book. And you see one example to the right of the slide. So this is a limit order book, and it consists of quantities and prices. The red ones that you see are basically sells. So these people want to sell at these prices. And the green ones are buys. So these people want to buy at these prices. The structure of a limit order book, which is basically used on the New York Stock Exchange, the NASDAQ, and also on centralized exchanges for digital assets like Coinbase, basically accepts offers to buy or sell these quantities at the prices that you see. And then how it works is that whenever there is a crossover, so whenever there is a pair of mutually acceptable orders, then this is matched and the order is executed at the price. Now, the parties whose limit orders sit there in the book, they're called market makers. And so this is some terminology that will show up also later. The issue with this mechanism is that basically it's costly to store and compute because you need to perform all of this constant matching, and you need to maintain all of these orders that are sitting and maybe getting canceled all of the time. And also, it requires active participation by these market makers. So it's basically hard to trade assets that have low liquidity, which are common on the blockchain and are called long tail assets. So AMMs are basically the most popular exchanges that live purely on chain. And you might have heard of them But how they work is that they have liquidity providers who supply these pools of assets. Again, a running example is going to be that of Ethereum and USDC. And you can see an example on the slide here. So for example, here we have a pool that has 3 Ethereum and 12,000 USDC. And they're inspired by the use of automate market makers for prediction markets, as Hansen first showed. So you have these two separate files of reserves with each of the asset. And then the AMM gives you a set of allowable trades, as we call it. So a menu of options that you can select from. And this trade that you select will result in a different pile of reserves in the AMM. So you could have a succinct description of this set arising from a formula, and you'll see this in detail by Samak on the second part of the tutorial. And anybody can choose their favorite trade out of all of these allowable trades. And so this will change the level of reserves in the pool, and the difference is what the trader will get or give. So let's look at the following example on the slides. We have two allowable states in this AMM, and potentially, of course, many more as well. The first allowable state is that contains 3 Ethereum and 12,000 USDC, and the second allowable state is that with 2 Ethereum and 18,000 USDC. One can choose to transition from the first state to the second state. And how the trade will happen is that the difference will go to the trader. So the difference of 3 minus 2 ETH is what the trader is going to get. And that trader is also going to have to give to the pool the difference in the reserves of the second asset. So that's the 6,000 USDC, plus some trading fee that will be some percentage of the whole trade. I won't focus exactly on the format of this fee in the talk. So basically, you can see that this is one example transition. And let me focus now on what you actually need to store for this AMM to work. The only thing that you actually need to store is the current level of reserves, right? So regardless of how many trades have been performed in the market, the only thing that you need to store is the current state. So for example, 2 Ethereum and 18,000 USDC. So it's a very economical market structure, but regardless of how many trades you have, you only need to store basically 1 or 2 numbers. Now, how is this menu of allowable trades actually changing? Well, in an AMM, this menu of allowable trades only depends on the current reserves. So consequently, the key feature of an AMM is that it changes prices depending on the trades that are executed on it and no other information. So whenever you have a trade, this changes the reserves in the pool, and therefore the AMM price that's provided is also going to change. And there's 2 relevant notions of price for us that will go into further detail on the other parts of the tutorial. The first one is the spot or marginal price of the AMM, and this is the price that a trader would get for an infinitesimal quantity of Ethereum traded, let's say, before the trade. And so this would be, in this example case, 4,000 US dollars. Then there is also the average price that is actually paid for the trade. And so here we can see that the trader actually gave $6,000 to get 1 ETH out of the pool. So the average price that the trader actually got for this trade is 6,000. And then there's also the spot price of the AMM after the trade. So how much it would cost to obtain an infinitesimal quantity of Ethereum from the pool after the trade. And that would be, in this particular example, $9,000. So you can see that as the reserves actually change in the pool, the price, the marginal price actually ends up also changing, and the average price is different than these prices. Now, a key feature of these markets is that the AMM actually does not react to information as external conditions change. So the price can grow stale as external conditions change. Let's say that there is some other market that offers some price for the asset, but the AMM only varies its prices with the actual executed trades on it. So that's the key feature of the AMM that we talked about previously. So what happens if there is an external market that actually does offer a different price than the AMM? And so if the average price that someone can get on an AMM for a particular trade is different than the external price. On our previous example, if we had also, let's say, Coinbase that offered a price for Ethereum of $9,000 per ETH, then we can see that the previous trade was actually executed for $6,000. So that would be that this party who would actually transact both on the AMM and on Coinbase would actually obtain a profit that is the quantity of Ethereum that they got, that is 1 Ethereum in our example, and the price difference on these two prices. So the external price is going to be 9,000 minus the average price that they got, which is 6,000. So they would obtain a profit in this way. In general, this is called adverse selection, and is basically due to trading with better informed traders. So these traders that actually have the knowledge of the external market, they're called arbitrageurs, and they actually can obtain a profit because the AMM does not actually react to this external information. So what is the cost of this adverse selection in AMMs? This is actually what we're going to talk about, and it's called loss versus rebalancing, LVR, as it's pronounced. And we actually established this on this paper that you see on the slides. And it actually is the dominant way that practitioners now think about adverse selection on AMMs. So as we said previously, adverse selection is the losses that are caused from better informed traders. And an example of that is when the AMM spot price is actually not up to date with external markets that contain some other price. So concretely, let's now talk about the empirical version of LVR. So coming up on the third part of the tutorial, Tim will also show you how you can use the most well-known asset price model to derive neat closed-form formulas for LVR that can even be used to predict ahead what the adverse selection costs are going to be. So what did we previously say that these losses to informed traders are? We said that it's the quantity that they actually trade on the AMM times the price advantage that they got. So the difference between the external price, the market price, minus the average price that they got from the trade. So this is exactly what you see then on the slide that we define as LVR. LVR is literally the sum over all of the trades that are executed on the AMM of the amount of, let's say, Ethereum that was sold on each of the trades times the difference between, on the one hand, the market price that you have during this trade, or after this trade rather, and the AMM price that you got on the AMM for this trade. So this is what is going to be defined as LVR. Another key feature is that LVR actually captures the adverse selection cost due to liquidity providing, and it's basically dependent on the price trajectory. So it depends on what the actual external market price are going to be throughout the set of these trades, and it accumulates on a trade-by-trade basis. So it's basically a positive quantity that is obtained throughout the trades, and it can only grow through time. And now a proposition is that what this quantity captures is that it also captures the profit that is extracted by arbitrageurs besides these adverse selection costs, and in particular the maximum profit that is going to be captured by arbitrageurs. So now what we basically understand is how much these arbitrageurs make. And now we want to circle back to the main question, which is basically what the liquidity providers make. So this will allow us to basically think about empirics and look at actual pools. So the observation is that liquidity providers are actually subject to a risk. And the reason that they're subject to this risk is because they hold some assets that are the assets that are contained in the pool. And so the assets that are contained in the pool may actually change value potentially dramatically. And so what one would actually want to do is that they would like to actually remove this price risk. And so how can you actually do that? Well, if you actually have a risky asset, then a way to counter that risk would be to basically keep the negative position of this asset. So this is basically called to short the asset at every moment in time continuously. So by keeping a negative position on the asset through time, what you actually cancel out is this price risk that the price changes without you being able to adjust your value. So what ideally one wants to do is have a position as a liquidity provider, and then also always keep the negative of however much risky asset the pool actually has. And this way, whatever price move actually happens does not affect you. This is what we'll call hedging. And this is the third interpretation that we see of lever is this hedging of the market risk. So the previous two interpretations that we saw is basically adverse selection costs, to recap. Secondly, the profits of our arbitrageurs. And now we're seeing what the effects on the liquidity providers are. So let's say, for example, that the price at an external market actually increases. According to what we've said until now, this means that an arbitrageur will actually now try to buy ETH from the AMM, whose actual price is stale and has not been updated yet. And so by the arbitrageur actually going to buy Ethereum from the pool, the liquidity providers are going to gain the fees that arise from this trading. So let's say that's some proportion, let's say 30 basis points. So a basis point is basically 1/100th of a percentage point. So 30 basis points, basically 0.3% would be of the pool value. That would be a gain for the liquidity provider. The liquidity provider would also gain the value of the Ethereum that got sold to the arbitrageur at the pool prices. So basically, since the rule of the AMM determines how much US dollars goes back into the pool, this is the value that the liquidity provider will gain from selling this ETH to the arbitrageur. And then also because we have this hedging position, what we also would have is that we would also lose the value that this negative position has. So why do we lose value from this? We lose value from this because since the external price actually increased, the short position, that is this negative position as we call it, actually loses the equivalent amount of value. And so the total actually LP returns after hedging, so after removing this market risk, is going to be the fees that you obtain minus lever. Now, I haven't shown you formally why that is, but I hope you can believe me when I say that this is actually the correct quantity that you would obtain by doing this. And so this will allow us very easily to take the model into data and basically evaluate it on actual pools that we have. So let's now focus on how you would actually evaluate it on a real pool. What you're seeing here in the slides is basically the Uniswap. So Uniswap is an example of an automated market maker that you see in the second part of the tutorial, exactly how the set of allowable trades for this market is defined. It's also called a constant product market. And so here you see the Ethereum USDC pool for this automated market maker, Uniswap V2. And specifically, what we're going to be interested here in is going to be the hedged returns of the pool. So what the liquidity providers of the pool actually obtain. Based on the interpretation that I talked about before, you can actually very easily evaluate the returns of the liquidity providers in an AMM pool with only a couple of additions and multiplications. And so the method that we talked about before, what is it? It is that at a regular interval, let's say, for example, 5 minutes, here on the empirics, you can also see various other intervals like 1 hour, 4 hours, and maybe even a day. What you'll actually do on every time that this interval occurs is that you'll get the external price. You'll also see what the pool value is, and you will subtract from the change of the pool value that you see this difference that the hedge is going to cause. So the difference that the hedge is going to cause is going to be this external price times the difference in the risky asset that your pool has. So what you'll actually do is that you look at how much Ethereum the pool has every 5 minutes, let's say, and this quantity that you subtract will be the difference to how much ETH the pool previously had times the external price. And the punchline on this is that basically it's very straightforward to take levered data and evaluate in an ex post fashion these hedged returns of the liquidity providers. So I hope that we got a good conceptual overview of AMMs and lever over this. And coming up, Siamak is actually going to show you the mathematical details that go into characterizing the AMM design space. And later, Tim will get into the actual maths that are behind the lever calculation.